Now, a dynamic RAM, which is the high-capacity memory system that you guys buy when you buy your laptops or your home machines, or you use one of the machines in the cluster, is much simpler. It involves a single field effect transistor, which is the access FET, and the storage is accomplished by simply putting charge on a capacitor. Right, and there's a lot of work to make those capacitors, have as much capacitance as possible, but in as small an area as possible, so that because I want the much capacitance in order to have the value that I'm trying to remember last a long time. So there are all these little leakage currents going on, and the bigger the capacitor, the longer it will take before that value leaks off. I would like, however, for the cell to be as small as possible so I can fit billions and billions and billions of them onto the little chip I want to build. And so you start getting very strange looking structures. I don't know how well you can see this in the slide. This sort of looks like a rotten tooth, right? And what it really is this is a cylinder where there's an internal metal cylinder that's been covered by a dielectric insulator, and then there's another plate of the cylinder, there's another metal plate that's gone on top of that. So I've made this cute little metal dielectric metal sandwich, which is basically a very small capacitor. Nowadays, memories are built with trenches. Same idea. You build a deep trench into the silicon wafer. You line the inside of the trench with metal, and then a layer of insulator, then another layer of metal to build these capacitors. These capacitors aren't very big. They do leak as time goes on. And so what happens is that I have to come back. The reason they're called dynamic is that once every 10 milliseconds or so, I have to come back, read the information off the capacitor, and rewrite it. Otherwise, I'll lose the information that's there. So every 10 milliseconds, circuitry in your computer is basically reading out every location in your main memory system and writing it back in again. So it's like the old Chinese, a circus act where you see the guys spin the plates, and they start spinning plates, and he's got 40 plates going, and then all of a sudden the one at that end is starting to wobble, and he runs back to spin that one a little faster and keep all the plates balanced. Well, that's what your dynamic memory system is doing for you behind the scenes. This is an inherently slow process. There's not much charge here, so it actually takes a fair amount of time to read a piece of information out of this cell. And the circuit itself involves these word lines are quite long. There's billions of these little cells in one of your memory chips. So this piece of circuitry is actually not as fast as one would hope. So to increase its throughput, we're going to pipeline it. You know how to do pipelining. And so, in fact, what we do is we send over the address often in a couple different groups. Now, we don't send in one clock cycle, we don't send all the address to the memory. We send about half of the address, and the next cycle we send the second half of the address because we don't really need it here as quickly as one might think we do. And the whole process of decoding the address and selecting the word lines and reading the information out of the memory cells, and then selecting which ones to send back to which one of these. We're often reading, in this case, hundreds and hundreds of bits in parallel, and then selecting the 32-bit quantity we want to send back. So this is a so-called synchronous dynamic memory. Synchronous because it's busily pipelined. And the so-called DDR RAMs that you all have in your machines use a clock transmission protocol where on both edges of the clock we're sending information. So this is really the bottleneck. The reason your machine is as slow as it is because getting information to and from the memory system is pretty much what's limiting the performance factor. So even with all this engineering of a pipeline system and using both edges of the clock to transmit data, this is sort of going to limit us. Okay. The trouble with this memory system actually has reasonably high throughput. It can sort of keep up with the consumption of the processor in terms of instructions, but sadly, it has a long latency. Once I have an address here, getting the first the first piece of data out of the memory is slow. After that, I get words, every couple of nanoseconds. But getting that first word out can take quite a while as it it gets processed through the pipeline.
Sure.
Yes?
I might be mistaken, but it seems that not all paths here go through the same amount of data.
Well, I think the goal is for them to actually do that. What happens is that the address gets decoded, right? So there's sort of, if you sort of follow an address through, right? Well, if there's a bug in the ARCs, I apologize. But yeah, clearly for all the usual reasons, we need a well-formed pipeline here. I'll look more at that diagram to see if I can find your bug. Okay.